Welcome to the Earth Science Classroom. We are looking at the Earth's interior today, and we have finally made it into the center of our planet, looking at the inner core and its characteristics, its location, how we discovered it, and all the things that kind of helped form it when the Earth was just being formed itself. So let's look at the location. Okay, so if we go down basically through the Earth, about 3,958.8 miles, or about 6,371 kilometers, we will reach the center of the Earth right here. So right here is the center. Okay, and that is a distance of a long way. So, and it's the surface. So right smack in the center, we have our inner core, and the boundary of the outer core, inner core, is around 5,100 kilometers. And on the outside, we have the outer core, which different video discusses its functionality, its characteristics, but it's basically a hot molten iron alloy with a tiny little bit of nickel and sulfur in there, and it is slowly revolving around this central inner core. So how did we discover this? So we can't exactly say that we've been there and we've directly sampled the core and figured out the environment and the composition and dimensions. No, what we've done is with most or all of these layers of the Earth's interior, besides really the crust, because we live on it and we can directly access materials from the core to figure out its composition and details, we've looked at seismic waves, which propagate from earthquakes, and they travel throughout the interior, and they change speed when they go through different mediums. When I say mediums, I mean states of matter or different density of materials, or even different materials itself, even different kinds of rock, from igneous to metamorphic, but are different kind of characteristics in which mostly the P wave, which is the first wave to be released, or the fastest wave, so it goes basically, it reaches its destination faster, and also the S wave, which is the shear or secondary wave. So, as I mentioned earlier, we can cancel out the application of using the S wave, because the Gutenberg was called discontinuity shows, or basically highlights, that the P wave at the mantle core boundary, basically the starting point for the outer core, there is a 40% reduction in P wave velocity. So it gets slower by 40%, and it goes through this different medium. And S waves are completely blocked from entering the outer core. Therefore, we can't use S waves to decipher or figure out what the inner core is, but we use P waves. So actually, there's one T there, not two T's for Gutenberg, and that was 1914. And then it took about 22 years, pretty much, 22 years. And another scientist by the name of Lehman basically saw that there was obviously there's a shadow zone where the P wave is deflected and refracted by the liquid outer core, causing the P wave to slow down and therefore basically be received on the other side of the Earth at a different angle than what it would if there was no outer core that's liquid. If it was a solid outer core, then there would be a different point on the Earth's surface where they would feel the earthquake. But because there's an outer core that's liquid, it's refracting the seismic waves and causing a shadow zone. So in this shadow zone, where there is no or very, very weak P wave P wave movement or P wave location, then Lehman figured out that there would be more shadow zone if the whole core was indeed liquid, like Gutenberg had discussed. But there was weak P waves within the shadow zone, so 104 degrees to 145 degrees. So there was weak waves there, and the weak waves gave Lehman an idea that there was something else that was deeper down that was changing the seismic waves to make them go change velocity and change the angle in which they would be received by the Earth's surface. So Lehman suggested that the inner core is solid rock, and that would account for the weak P waves being registered in the shadow zone and the location of those P waves as well. And a secondary discovery was that the P waves towards the bottom or lower end of the outer core would actually increase in velocity. That would suggest that there was a different density or different state of matter that these P waves were traveling through to increase velocity. And the only way that we know to increase velocity is to increase the density of that material in which it's going through. So if it's going from a liquid to increased density, then we must assume that it is a solid material that it's going through. So Lehman made this big discovery, really, that using the indirect information from seismic waves, we could postulate or figure out that the inner core exists and that it's solid. So once this was established, scientists started to do some more experiments and more estimations on this newly found inner core and what it could be like, its characteristics, what it's made of, its composition, its origin, its history. Has it always been there? Has it formed recently? That kind of thing. And first, we looked at the density. So looking at other planets and other stars, using astronomy and using what's around us in our solar system, we can figure out more about our planet. And we averaged that the average density of the planet is 5.5 grams per centimeter cubed. And that's all well and good, but then it led scientists to think, well, that's kind of an average density that's kind of high. It's kind of a higher number than you expect because the mantle is around 8% volume and the mantle itself is a lower density. The majority of the Earth is between 2.7 being the crust to around 3.5 or even 4.5. So the majority of the Earth is around this density. In order for the average to be pulled up to a 5.5 means that there must be something really heavy in the center that would skew the average more towards 5.5. So the inner core had to be really, really dense in order to create this 5.5 average. And then they started thinking, well, what could cause this dense this density, and what material, what composition would mostly be accountable for this? And looking around in our solar system, the densest and most common is iron. Now we have iron in the crust, we have iron coming up from mantle plumes, we have iron coming through different areas of the mantle, and obviously with the outer core being liquid iron alloy and nickel, it made sense that there was a concentration of iron and nickel in the inner core. Now, it can't just be iron, because tests on iron at the surface and under certain pressure and temperature, iron does not account for the extreme density. Had to add in nickel to the mix in the composition in order to make it the right density to average out to 5.5. So now we're working backwards from the average density and figuring out that the core is this solid iron nickel alloy, okay, and that it's very, very dense. So the density is 12.6 grams per centimeter cubed, up to make some room here. Oops. Up to around 15.5. So extremely dense in comparison. So again, we use this because water is 1 gram per centimeter cubed. So it's going to be up to 14 or 15 times denser than water. And that's no surprise, being the characteristics that we started to learn about the inner core. So let's work on the characteristics, the amazing, awesome facts about the inner core that we are discovering every time we look at it in different experiments. And the temperature itself is insane. Looking at between 6,000 and 6,700 degrees Celsius, which is comparable to the surface of the sun. The PSI, the pressure, which is insane, the lithostatic pressure, which comes from the weight or mass of a rock above plus gravity. You're looking at the center is about 52 million psi. It's 52 million pounds per square inch. That is 128 Boeing 747 jumbo jets pushing down on every square inch of the inner core. That's insane. The depth, you're looking at 5,100 kilometers under the ground to 6,371, or around 3,984 miles. The mass, we're looking at about 33% around mass, about a third of the mass of the Earth, even though it's only 16.4% volume. So that goes back to saying that it's extremely dense, therefore, but also not large, not a large portion, but it's a very dense, small ball of iron nickel alloy. So the next video, look at the origin and the heat of the inner core, and think about what's going to happen in the future and what happened in the past, how it formed. So hope you guys enjoyed this video. Hope it looks at the inner core and how we can suggest this to our students, and how we can present it as like a fact-finding mission of how we figured this thing out. That's 4,000 miles beneath our feet. And please subscribe if you like the video and leave a comment.